In this nugget, you and I get to lab up from scratch an environment where we can implement and verify dynamic multi-point VPNs. Let's begin. Because this is our first nugget with content, I want to share with you some housekeeping rules. Number one, the Nugget Lab files, which are associated with this course that you can download from the CBT Nuggets website. They are usually going to include the diagram for the current topology that we're working with, as well as all the commands that we're using in the nugget. Because my goal is to give you all the tools so that you can lab this up and build it on your own. And you could build it inside of a GNS3 environment, or inside of Viral, or work with live gear, or if you have a simulator that supports all the commands, it really doesn't matter which method you use as long as you get that hands-on practice. And that's what the nuggets in this course are all about, is practicing hands-on. The iOS image I'm going to be using for most of these videos is this guy right here. You do not have to use iOS version 15. You can use iOS version 12. As long as the feature sets include the features that we're using in that nugget. So in the case of this nugget, we're going to be using dynamic multi-point VPN. So you'd want to have an iOS image that supports those commands and features. The other thing I want to share with you right up front is that my default interfaces and modules that I'm using in the 7200 series router. So in slot number 0, I've got a couple of fast Ethernet cards. In slot 1, I've got some gigabit. In slot 2, I have a 4-port serial. And in slot 3, I've got 4 10 megabit Ethernet interfaces. And you don't have to use those exact same interfaces, but if you do happen to use those exact same modules, you can replicate what we're doing together in the nuggets in your own practice lab. And if you are brand new to GNS3, I would also refer you to the GNS3 1.x Fundamentals course. And it can assist you in getting up to speed very, very quickly with the fundamentals of GNS3 version 1.x. And GNS3 personally is what I'm going to be using most of the time in this course as we go through these nuggets together. For training regarding the details of DMVPN, I would refer you to the CCNP route course taught by my good friend Jeremy Chara. That's course number 300-101. Our focus here in this nugget and in this course is to do hands-on labs. And if you've been through that DMVPN nugget with Jeremy and CCNP route, and you want to take a look at adding the IPsec on top of the DMVPN, I would invite you to join me in the 300-209 course, which is the SIMOS course. It's part of the CCNP security. And there is a nugget specifically called Protected DMVPN, and it just focuses on adding the IPsec cryptography on top of a working dynamic multi-point VPN network. Let's take a look at the details regarding this topology that we're going to build together. And again, this diagram is available as part of the Nugget Lab files if you'd like to download it and have it open on a separate screen. The NBMA addresses, which I also like to think of as the globally reachable addresses that we're going to use in our simulated internet, is the 14 network, the 24 network, and the 34 network. And one of the inside scoops of why I'm numbering it that way is that the internet really is just another router R4. So 1.4 is between router 1 and router 4. Network 2.4 is between router 2 and router 4. And network 34 is between router 3 and router 4. At the headquarters site, we have the 10.1.1 network. At the R2 spoke site, we have the 10.2.2 subnetwork. And we have a site with router 3, which has the 10.3.3 subnet. Our host address on the 10.1.1 network is .11. On the 10.2.2 network is .22. And on the 10.3.3 subnet, our host is going to have the 33 host address. Also, wherever it's not shown, the router number is going to be the last octet of the router. So R1 is always going to end in .1, R2 is always going to end in .2, and R3 is always going to end in .3. For our GRE interfaces, for our tunnel 0 interfaces on each of these routers that we're going to build, we're going to be using the address space of 172.16.0. And again, the last octet, or R, refers to the router number. So R1 will be .1, R2 will be .2, and R3 will be .3. So in building our topology from scratch, I'm going to use GNS3. Again, you could use Viral, or you could use live equipment, or some other simulator if it supported all the features and commands. So let's bring out our routers first. Let's go ahead and bring out router 1, and then we'll bring out router 2, and router 3. And for the internet, I'm going to drag out router 4 that is going to be directly connected to R1, 2, and 3. Then we need some PCs, so we'll grab the virtual PC simulator and drag out PC1. Let's drag out PC2, and we'll drag out PC3 as well. And then we'll connect it all together following our diagram here. So we'll click on the link tool, and from PC1, we're going to connect it over to Fast Ethernet 00 on R1. I'm also going to turn on the labeling tool so we can see those interface labels. From R1 to our internet, which is R4, we're going to use interface 3/1. Now I am going to be using 3/1 on both sides. So in our topology, interface 3/1 on R1 will go to 3/1 on R4. The reason, the inside scoop of why I'm using Ethernet interfaces instead of fast Ethernet or gigabit is that sometimes in GNS3 with this iOS image, sometimes when I use IPsec or have a lot going on, there's some checksum errors that occur. And so I've found that by using serial interfaces and Ethernet interfaces, that those mostly can be avoided. Your mileage may vary. You may never have a problem. But while I'm doing demonstrations, I really don't want checksum errors to come up because they distract from the learning. So from R2, let's go ahead and grab the Ethernet 3/2 interface and bring it down to R4 to its interface 3/2. And from R2 out to PC2, we'll use Fast Ethernet 0/0. And then from R4, our simulated internet, we'll use interface Ethernet 3/3 to go over to R3's interface 3/3. And our last connection is from R3's FA00 going over to our PC3 with the virtual PC simulator. So we can turn off our connector tool, and if it makes us feel better, we can right click on R4 and we can select change symbol, and we can scroll down and select the cloud option right here, and then click on OK so it can look like a cloud. And with that in place, we'll start all of these devices by using the start icon in the toolbar. And then we'll connect to all these devices by clicking on the console icon, which will open up a console to each and every one of these devices. And again, for the basic mechanics of how to get up and running very quickly with GNS3 in general, I would recommend, if you haven't yet or you're new to GNS3, take a look at the GNS3 1.x Fundamentals course right here at CBT Nuggets. So we're going to start right here, and this is router 4, has 3 Ethernet interfaces. And because those are the only 3 addresses we're using as globally routable addresses, that means R4, acting as the internet, has reachability to all that global address space. So on router 4, our simulated internet will go into configuration mode. We'll go into interface config for interface 3/1. We'll put on a quick description to remind us what this interface is connecting to. Then we'll give it the IP address of 14.0.0.4 with a 24-bit mask, and we'll bring it up with the command no shutdown. Next, we'll make a road trip over to interface 3/2. We'll give it a quick description to remind ourselves of what it's doing. We'll give it the IP address of 24.0.0.4 with a 24-bit mask. And then we'll bring it up with the command no shutdown. So we've got 2 of our 3 interfaces. We have 1 more to go. So our last interface is interface Ethernet 3/3. We'll give it a description as well. And we'll give it the IP address of 34.0.0.4 with a 24-bit mask, and we will bring it up with the command no shutdown. So now our internet, or R4 in our case, is perfectly set. We don't need to do anything else on R4 except let it route between those three networks. Next, let's make a road trip over to Mr. R1. And on R1, we'll go into configuration mode. We'll go into interface FA00. That's the left interface facing its private network. We'll give that interface the IP address of 10.1.1.1 with a 24-bit mask, and we'll bring it up with a no shutdown command. Next, we'll address the interface that goes over to the ISP. So we'll go into interface Ethernet 3/1 and give it the IP address of 14.0.0.1 with a 24-bit mask, and we will bring it up with the command no shutdown. Now, most devices, if they're connecting to other devices on the internet, are going to need a default route, and that is no exception with R1. So on R1, we'll create a default route that says if you don't have a more specific route in your routing table, the next hop is 14.0.0.4. And 14.0.0.4 is the IP address on R4, who's acting as our internet service provider, and in our case, the entire internet for our topology. Next, on R1, let's create the new tunnel interface. Now, by default, a tunnel interface is going to be using GRE encapsulation. So we'll go into interface tunnel 0, and we'll say tunnel source Ethernet 3/1. Now, we have a couple options here for this tunnel source. We could specify the literal address that's sitting on that interface of 14.0.0.1, or we could simply point to the interface itself, and then it will extract the IP address from that interface to use as the source for this tunnel. Either way works. If our spokes were dynamically assigned addresses, we would definitely want to refer to the interface numbers, as those dynamically assigned IP addresses on the spokes could change from time to time. And when they do change, we'd like our configuration on those spoke routers to still work. We're going to specify that we want to use GRE multipoint, and we're also going to specify a GRE key of 6783. And that key would need to match on each of these spokes as well. As Jeremy explained in the CCNP route course, the magic behind dynamic multipoint VPNs is GRE multipoint interfaces and the next hop resolution protocol. So we're going to specify an NHRP network ID of 1, which also has to match on the other devices, R2 and R3. We've also specified a password we're going to use for authentication of Cisco 123. And we're also using on the hub the IP NHRP map multicast dynamic, which we need on the hub router in a DMVPN configuration. Next, we'll give this interface, this tunnel interface, an IP address of 172.16.0.1 with a 24-bit mask. And when we set up R2 and R3 respectively, we'll use .2 and .3 on the 172.16 network for their GRE interfaces, for the tunnel interfaces. If we want to go ahead and tweak the MTU as well as the maximum segment size for TCP, we can do that as well. These are optional, not required. And in a production environment, you may need to do some tweaking to find the sweet spot for those. And normally, whatever the MTU is, you'd want to have the adjust MSS size about 40 bytes below that. So our numbers of 1400 for the MTU and 40 less than that for the TCP adjust MSS of 1360 is perfect. We're going to use EIGRP as our routing protocol to advertise routes across the GRE tunnels. And as we do that, I want to make sure that when we're advertising routes that we don't put our own IP address as the next hop if we have a multi-point network. For example, we have R1, R2, and R3 that are all going to be on the 172.16 network. And the command no IP next hop self EIGRP1 will allow R1, when he's learning routes from R3 as an example, and advertising those up to R2, to not replace the next hop with its own IP address. It can go ahead and leave on R3's address from that 172.16 network. And there are a boatload of options that we can tweak with and play with DMVPN, including DMVPN Phase 1, 2, and 3. So this is just one of the nerd knobs that we can tweak. The other option we're adding here is the no IP split horizon for EIGRP autonomous system number 1. And that's because we want R1, when he receives the route of 10.33 and he receives that on his tunnel 0 interface, we also want R1 to be able to advertise that back out up to R2 off of that same tunnel 0 interface, which is our multi-point GRE tunnel interface. And if split horizon was on, which it is by default, R1 wouldn't bother to advertise that route back out that same interface, so R2 wouldn't learn about the 10.33 subnet. Now, one of our challenges is that we've just told this interface about EIGRP autonomous system number 1, but that autonomous system doesn't exist yet on this router, so we need to configure that as well. So let's create router EIGRP1. We'll throw in network 10. That'll cover our private network, and we'll also throw in network 172.16, which will cover our GRE network with our tunnel interfaces. I'm also going to toss in no auto-summary. Now, I am running iOS 15, and auto summary is off for EIGRP by default. However, if you're labbing this up with iOS 12.x, which is perfectly fine, your auto summary may be on by default. So I'm just erring on the side of caution. That way you can follow these same exact steps and have successful results, regardless if you're on iOS 12 or iOS 15. Next, let's make a road trip out to our good friend at the top of our topology, R2. We'll go into configuration mode, interface fast Ethernet 00, which is facing our PC on that subnet, and we'll give that FA00 interface the IP address of 10.2.2.2 with a 24-bit mask, and we'll bring it up with the command no shutdown. Next, we'll configure the interface between R2 and our service provider, and that's interface Ethernet 3/2. We'll give it the IP address of 24.0.0.2 with a 24-bit mask, and we'll bring it up with the command no shutdown. Let's tell R2 to use R4 as its default route with the command IP route quad zeros space quad zeros and the next hop of 24.0.0.4, which is R4's Ethernet address that's facing R2. Next on R2, let's create the tunnel interface. So interface tunnel 0, we could actually number it something other than 0, but we're going to use 0 as a starting point. We'll tell it that it's going to be using GRE multipoint, and that the source of this tunnel is going to be the IP address on its Ethernet 3/2. We'll also supply the tunnel key it can use in combination with this tunnel interface. Next, let's specify a few of our NHRP commands, the next hop resolution protocol. Let's use network ID of 1, and for authentication, let's use the password Cisco123, which again needs to match if we want to have successful authentication for NHRP with other devices. Next on the spoke, we're going to use the command IP NHRP map multicast and point to the globally routable address, the NBMA address of R1, which is 14.0.0.1. And that's the IP address of our hub. Next, on R2, we're going to do a manual mapping that says, okay, to get to 172.16.0.1, which is the GRE tunnel interface of R1, the mapped address is the reachable global NBMA address of 14.0.0.1. So on this spoke, we have that single static mapping that associates the global address, the NBMA address of 14.0.0.1, with the hub's GRE tunnel address of 172.16.0.1. And we're going to follow that up by telling this router that the NHS, which is the next hop server for NHRP, is at 172.16.0.1. Next on this interface, let's give it an IP address of 172.16.0.2 with a 24-bit mask, and we'll play the MTU and the TCP MSS adjustment game of 1400 and 1360, and then we'll exit interface configuration mode for this new tunnel interface that we've just created and configured on R2. Let's also configure EIGRP for autonomous system number 1. We'll include network 10, which is the local network that R2 is supporting, as well as the GRE network of 172.16. And we'll put in the no auto summary as well in case you're following along with iOS 12.x. Next, let's configure R3. We'll do this one a little bit faster because it's virtually identical to what we did on R2, except some of the IP addresses have changed to reflect the IP addresses owned by R3 compared to R2. So on F800, we've given it the IP address of 10.3.3.3 with a 24-bit mask, and we brought it up. On interface Ethernet 3/3, which is facing the internet, we're going to give it the IP address of 34.0.0.3 with a 24-bit mask and bring that interface up as well. We'll give R3 a default route with the command IP route quad 0 space quad 0 and then the next hop address of R4, which is 34.0.0.4 from the perspective of R3. Next, we'll create our tunnel interface. We'll specify tunnel mode GRE multipoint because that's what's used by DMVPN. We'll specify the tunnel source as our IP address on Ethernet 3/3, and we'll specify the tunnel key of 6783, which happens to be my CCA number. And that makes it easy for me to remember that number. Next, we'll put in our NHRP commands, the network ID for NHRP, the authentication key we want to use of Cisco 123, the IP address of 14.0.0.1 for multicast traffic, the mapping that maps the global address to the GRE address of the hub, as well as telling it where the NHS server is, which is the GRE interface address of the hub. So on this interface, we also need to give it an IP address. Since we're on R3, we'll use the address of 172.16.0.3 with a 24-bit mask. We'll adjust the MTU just because we did on the other two to make it consistent. We'll also adjust the MSS to 1360, which is 40 below the MTU. Our last step here on R3 is to enable EAGRP Autonomous System Number 1. We'll use Network 10 and Network 172.16 to bring in the local and the GRE interfaces into and make them part of EAGRP. And we'll turn off auto summary as well. And you'll notice from this console message that we have a neighborship between us, R3, and R1, the hub. Next, let's go to our PCs. We'll go to our virtual PC number 1. And on PC number 1, let's give it the IP address of 10.1.1.11. The syntax is IP 10.1.1.11 space /24, and then the IP address of the default gateway we want this PC to use. So PC1 has been configured to use R1 as its default gateway. Let's go to PC number 2 and do similar treatment there. Here on PC number 2, which is hanging off of R2, we'll give it the IP address of 10.2.2.22 with a 24-bit mask and tell it to use the default gateway of 10.2.2.2, which is R2's fast Ethernet 0/0 address. And because we don't want to leave anybody out of the party, we'll go to PC3 and assign it the IP address of 10.3.3.33 using that same syntax that we would with a virtual PC from the virtual PC simulator. Now, just for a moment, let's go to router R3. And on router R3, let's do a show DMVPN. And what this is saying in the output of show DMVPN is that we have a static mapping that indicates that if I need to reach, says R3, if I need to reach the tunnel address of 172.16.0.1, which is the hub's tunnel address, the NBMA, or the global routable reachable address I would use to get there, is 14.0.0.1. And that's from the mapping we applied in the tunnel interface of R3. Another fun command that we can issue right here is show IP NHRP. And here in the output of show IP NHRP, this is also referencing the mapping that indicates to reach 172.16.0.1, which is the tunnel interface of the hub. The NBMA address, or the global reachable address, is 14.0.0.1. Because there are so many possible flags, I included a document called dmvpnflags.txt, and it has the flags and their meaning. For example, if the flag said authoritative, that would indicate that the NHRP information was obtained from the next hop server or router, let me scooch over here a little bit, that maintains the NBMA to IP address mapping for a particular address. And then there's implicit and negative and unique and registered and used. So if you're interested in the flags, if you're labbing this up and want to take a look and see what those flags are and what they mean, this file, which is part of the Nugget Lab files, can be a nice, quick, easy resource for you to get at. So now let's have some fun with this. If we go to PC number 3, and we try to ping PC2 at 10.2.22, initially, because R3 hasn't yet resolved the 24.0.0.2 address that's mapped to the next hop of 172.16.0.2, the initial traffic is going to go to the hub and then out to the spoke. However, almost simultaneously, the NHRP will be in motion, the next hop resolution protocol, and R3 is going to be asking the hub, hey, what is the NBMA address, the global reachable address, to get to that next hop of 172.16.0.2? And so as the answer is fed back to R3, and R3 then learns, oh, the next hop of 172.16.0.2 is at 24.0.0.2, these two guys right here can dynamically build their own tunnel using that same multi-point GRE tunnel interface to each other. And one of the easiest ways to see that is let's do a trace out to 10.2.2.22. That's the PC hanging off of R2. And I'd like you to notice something. As we did that trace, this is a trace from the virtual PC simulator, look at this second hop. The first hop was the default gateway, which is R3. And the next hop was 172.16.0.1, which is R1's tunnel interface. And then it was routed back out up to R2. So the focal point here is that middle hop in our path. If we use the up arrow key and we issue that same command again, because in the background the NHRP resolution was being done and the dynamic tunnel between R2 and R3 is being built, the next time we do this, you should notice that the next hop is directly through R2. So the first hop is the default gateway. So PC3 use the default gateway as the first hop. And then R3 use the next hop of R2 at 172.16.0.2. It didn't bother sending it through the hub, and that's because these two devices, R2 and R3, now have a direct GRE tunnel between them using their multi-point GRE tunnel interfaces. So if we went back to R3 just for a moment, a few moments ago when we ran the command show IP NHRP, we had that single static mapping. If we use the up arrow key to issue the command show IP NHRP once again, notice now that we have two. The first one here is from our static mapping on the tunnel interface, and the second one is dynamically learned. And it knows that to reach the 172.16.0.2 address, which is the GRE interface of R2, that the NBMA address, the globally reachable address, is 24.0.0.2. And that allowed R3 to build that connection up to R2. And if we looked at R2, which I think would be a good idea to do, so we'll go over to R2 for a moment. And on R2, we'll issue the command show IP NHRP. It has this additional mapping that says, okay, the 172.16.0.3 address, which is the tunnel interface address of R3, and the next hop from an EIGRP perspective to reach the 10.3.3 subnet is reachable via the NBMA or global address of 34.0.0.3. And it learned that via NHRP. It was learned dynamically. And again, for the flags regarding the output of the show IP NHRP command, you can refer to that document I have as part of the Nugget Lab files. In this nugget, we've identified that in the Nugget Lab files, we can get the diagrams that we're using as well as all the commands we just did in this nugget to build your own topology. We also discussed the flavor of iOS that I'm using for these demos, as well as the modules and what's in those modules in this virtualized environment that we're setting up. We also identified two additional resources. Number one, for the basics of DMVPN. You go to Jeremy's course, 300-101, for the training on DMVPN. And if you'd like to take a look at implementing IPsec on top of a DMVPN network, you can check out the Protected DMVPN Nugget, which is part of the CCNP Security SIMOS, that's the 300-209 course, right here at CBT Nuggets. I have had a great time in this nugget. I'm so glad you joined me for it. I strongly encourage you to lab this up in your own practice environment, and that will assist you in building your skills and reinforcing the concepts regarding DMVPN. So, once again, I've had a great time. I'm glad you joined me for this nugget. I hope this has been informative for you, and I'd like to thank you for viewing.